Let's go through activity 10. So in question number 1, we're going to explore the junk data set, and this is a data set from the late 90s when junk mail filters were just being developed. And the way that we're going to do this is to use word frequencies, so the fraction of words in an email that's money, buy, free, etc., as predictors as to whether an email is safe or if it is junk. So let's go ahead and add the junk data frame into our environment. And if we look at the junk data frame, we see that our variable that we're going to try to predict is called junk, and the two levels are junk and safe. Now, by convention, R is going to develop a model that predicts the level that comes last alphabetically. So our model is going to be predicting the probability an email is safe based on these word frequencies. These are the fraction of words in the email that are these words. And then also, if we scan way down, some ideas about punctuation, so the fraction of parentheses, the fraction of hashtags, the properties of capital run lengths, how many capital letters appear all in a row here. All right, so part A says the naive model predicts every email to be the majority level. So let's figure out what the naive model would do, basically majority rules, and we can get an idea for what the naive model would do just by looking at a summary of the data frame and just scanning up to see, well, what are the distributions of junk and safe emails in this data set. So the naive model is just majority rules. We see that the majority are safe emails in this data set. And so the naive model is going to make classification errors for every single junk mail message. It's going to predict everything to be safe. And so we can talk a little bit about the misclassification rate of the naive model. So we see safe is the majority level. So the naive model predicts every email to be safe, thus misclassifying the 1813 junk emails in the data set. So the misclassification rate, well, we have 1813 errors out of the 4601 total emails, which works out to be a fraction, just a little under 40% here, so 39.4%. So basically developing no model whatsoever, the naive model is going to have a 39.4% misclassification rate. So we better hope that whatever model that we develop does better than this. It has a misclassification rate that's lower. Part B tells us that a particularly strong association exists between the probability of being junk mail and the frequency of the word free. That makes sense. So let's fit a simple logistic regression model and talk about that. So I'm going to name my model M. We'll use GLM once again. We're predicting junk from just the single variable free. That's living in our junk data frame. And I know I have to turn on the logistic regression feature by saying family equals binomial. We'll run it. We get a warning message that says fitted probabilities numerically 0 or 1 occurred. That's fine. It's just giving us a heads up that, hey, there are some emails with such a high probability of being junk and such a low probability of being junk that R has to treat that as a 0 or a 1 due to constraints on machine precision. So, all right, let's look at a summary of the model. Let's visualize that model so we can see what the logistic curve looks like. And then also let's get the confusion matrix for the model so we can talk about how well it makes predictions. So if we get a summary, a visualization, and a confusion matrix, what can we talk about? Well, part B1 says true or false, emails that contain a higher fraction of the word free have a higher probability of being junk. All right, well, we can answer this by either looking at the output or looking at the plot here. And I think looking at the plot is always easier. What we notice is that if we compare two emails, the one with the larger value of free has the smaller probability of being safe, or in other words, the larger probability of being junk. So what we can take away from this is that emails that contain the word free more often have that higher probability of being junk. Emails that contain a higher fraction of the word free have a higher probability of being junk. So yes, this is true. Same sort of interpretation from looking at the summary output. Since we see the coefficient of free is negative and our level of interest, the one that comes last alphabetically, is safe, it implies that emails with larger values of free have a lower probability of being safe, which just translates into a higher probability of being junk. All right, so how well does this model make predictions? We can look at the confusion matrix. B2 asks us how many junk emails were correctly classified as junk. All right, well, we have this row that tells us information about the actual junk emails in the data set. There are 1813 of them. And it looks like our model predicts junk for 638 of them. So we get those right. How many safe emails were incorrectly classified as junk? Well, this row tells us something about the safe emails in the data, and it looks like 127 of them were predicted to be junk. So those are 127 errors that the model has made. What's the misclassification rate of the model? Well, there's two types of errors that this model can make. It can predict junk when indeed the email is safe, or the opposite. It can predict the email is going to be safe, but in actuality, the email turned out to be junk. So we can simply add up those two numbers, divide by the total number of emails, and that gives us the misclassification rate. So 127 plus 1175 over 4601. And that turns out to be just about 28%, so 28.3%. All right, so this simple logistic regression is outperforming the naive model in terms of misclassification rate. The simple logistic regression misclassifies a little over a quarter of the emails in the data, whereas the naive model misclassifies nearly 40%. So we do a lot better just by predicting junk from this single word frequency. All right, well, we've done a logistic regression model. What if it's not a reasonable reflection of reality? We should always make sure that the specific shape that we're imposing on the relationship between the probability and our x variable really is well described by a logistic curve. So let's check the validity of the simple logistic regression by doing two things. First, let's run associate, and that'll be y twiddle x, so junk twiddle free, data equals junk. And this will give us a very vague idea for how the probability of being junk and safe changes with our predictor variable. And so what this does is it basically splits up the unique values of x that was in the data set. And in this case, this bar right here represents all the zeros. A lot of emails didn't have the word free. And these two bars over here represent the emails that had a fraction that were bigger than 0 up to 0.4. And this last bar above 0.4 all the way up to 20% here. And it's tabulating what fraction are safe and which are junk. And so what we see is that, yeah, the probability of being safe gets smaller and smaller as the word frequency free gets larger. And so maybe that is well described by this logistic curve. It's a little bit hard to tell with one of these plots here. It's not easy to digest, and so that's why we actually rely on the results of a statistical test to determine whether or not the model is a reasonable reflection of reality. So we can just run check regression. And this will provide us with two tests, one that's easy to pass and one that's hard to pass. So what we see in this case is that both p-values are less than 0.05, implying that we have failed both tests for the assumptions of the logistic curve here. Now, that's a problem. So method 1, this is the test that is really, really easy to pass. And so if we fail this test, that's bad news. It's basically implying that the logistic curve is not a great description of how the probability of being junk changes with the word frequency free. All right, so we say no, the logistic curve does not provide a reasonable reflection of how the probability changes. The p-value of the, we'll call this the goodness of fit test, method 1, is less than 0.05. In fact, it is 0. So, all right, the logistic regression predicting junk from free doesn't really provide a reasonable reflection of how the probability actually changes with the word frequency, but we still see that it's actually pretty useful. So we know already going into this that all models are wrong, some are useful, so this logistic regression is obviously wrong, but notice that it still predicted the whether an email was junk or safe much, much better than using no model at all, using just the naive model. All right, so part D says that even when the logistic curve doesn't provide a reasonable description of how p changes with x, like it doesn't here, the model is still more useful than the naive model sometimes. So is the simple logistic regression model better? Well, we just answered this. We say yes, the misclassification rate of the simple logistic regression is about 28.3% compared to the nearly 40% misclassification rate of the naive model. So, all right, this model isn't the best for describing how the relationship with P and the word frequency changes, but it's actually a lot better than nothing when we try to make predictions. Party asks us to now fit the full model, so GLM junk twiddle dot, family equals binomial, and to talk about it. So let's run this model, and let's get a summary of the model. Let's check to see whether or not this model provides a reasonable reflection of reality, and then also let's look to see how well it makes predictions. All right, so looking at a summary, we get all the coefficients and p-values. We can talk at length about that if we wanted to. We can check the regression, and we can look at the confusion matrix. Okay, so let's look at what we're being asked to talk about. So among emails with otherwise identical word and character frequencies and capital letter characteristics, do emails with a higher frequency of semicolons have a larger or smaller chance of being safe? Well, okay, the output from the logistic regression tells us this because, remember, if we look at the coefficient of a particular predictor, like semicolon, this tells us something about how the probabilities differ between otherwise identical emails with respect to all the other predictors in the model, who just differ in that predictor variable. So since the coefficient of semicolon is positive and our model is predicting the probability of being safe, all else being equal, emails with larger values of semicolon have a higher probability of being safe. Okay, so emails with a higher probability, with a higher fraction of semicolons have a higher probability of being safe. Coefficient is positive. Is the association between these two variables statistically significant, even after accounting for all these other variables? Yeah, sure is. The p-value is less than 5%. Actually, it's 0.0035 here. All right. Question E2 asks us, is the variable make statistically significant in the multiple regression model? And that's up near the top of this list. It's a very long list. Here's make, and what we see is that the p-value is bigger than 5%. So no, it is not statistically significant. So make is not significant in the multiple regression model. P-value is 0.092. And we're being asked to fit a simple linear regression, or logistic regression, trying to predict junk from make. And why we're doing this? Well, it turns out that if we look at a summary of this model, we find an apparent contradictory result. We see that in a simple logistic regression model, make is highly statistically significant because the p-value is much less than 5% here. But it is in a simple logistic regression. P-value is 1.92 e to the minus 15 here. So we're asked, which is it? Is there an association between the probability of being safe and the frequency of the word make, or not? So in this case, well, this is the same sort of contradiction that we ran into with multiple linear regression here, where sometimes the variable is significant and sometimes it's not. How do we explain this away? Well, the fact that it is statistically significant in one of these models does imply that the frequency of the word make contains some useful information about the probability of being safe. Now, the fact that it's significant in the simple logistic regression, but not in the multiple logistic regression, must imply that whatever information the word make has about being safe or junk is redundant with the information that is provided by the other predictors. Remember, what the p-value in the multiple logistic regression model is telling us is whether or not adding in that variable significantly improves the model, basically adds in a significant new amount of information about our y variable. So basically any information that the word make has is contained somewhat in the other word and punctuation frequencies. And once we know those other things, we don't also need to know make. All that information is already represented in the model. So yes, there is an association between being safe in junk and the frequency of the word make, it is just the case that the information provided by make is redundant with the information already provided by the other word character frequencies. Adding it to the model with these other predictors doesn't provide any new information, basically. All right, does the multiple logistic regression model provide a statistically valid way of describing how the probability changes with these word and character frequencies? Well, if we look back at the results of check regression, we still see the two p-values are less than 5%. We fail them, and when we fail the easy to pass test, well, okay, yeah, that model is not a valid description of reality. It still might be useful for making predictions, but it's definitely not the way the probability is really changing with those frequencies. So the p-values of the goodness of fit tests are both less than 5%. In fact, they are 0. So no, the model does not provide a statistically valid description of how the probability changes with these predictors, but the model actually is quite useful for making predictions. Why is that? Well, looking at the confusion matrix, we see that the misclassification rate of this model is substantially lower than the naive model or the simple logistic regression model. So the misclassification rate is 122 predicted junk but in actuality safe, plus 194 predicted safe but in actuality junk over the total number of emails, which turns out to be 6.9%. So this is much lower than the simple logistic regression model or the naive model. And we see this a lot in business analytics. The models that we're using aren't exactly accurate reflection of reality, but they're still really quite good at making predictions here. And that's fine, because we know going into this that all models are wrong, but some can really be quite useful. We're never going to fully capture reality with a fairly simple statistical model here. All right, part F says that interactions may play an important role, and they very often do. Without interactions present, well, the model assumes essentially a one-curve-fits-all approach. The shape of the logistic curve describing the way the probability changes with our predictor variables is the same for all individuals. If we allow an interaction to be present in the model, then the shape of that curve can be different depending on the characteristics of what particular individuals we're talking about. Sometimes that curve might be really steep. Sometimes the curve might be changing slowly. So let's take a look at one specific interaction. So let's fit a logistic regression model predicting junk from you and direct along with the interaction, so we can put a star in between those two variables. Making sure we put family equals binomial so we get this right. And what we're going to do is we're going to run the summary of the model, and then we're also going to visualize the model. And we're going to change the x limits of where the plot is going, just to make the shape of the curve a little bit clearer. We're going to go from minus 15 to 15. Obviously impossible to get negative values, but this will make the visualization easier to digest. And then we're also going to put the legend in the left. So we can say lock equals, in double quotes, left. All right, so there's a summary of our model. The interaction is statistically significant. Let's look at what the model implies. And we can see this interaction, right in front of our very eyes here. We see that the nature of the relationship between the probability of being safe and, say, the frequency of the word direct is actually negative when the U frequency is large, but it's positive when the U frequency is small or achieves medium values. So the nature of this relationship changes really quite a bit. So is the interaction statistically significant? Yes. The p-value is 0.02093, which is less than 5%. For what value of direct, small, median, or large, is the relationship between p and u the strongest? So looking at the p versus u plot here, we see that the red curve changes the quickest, basically has the steepest part, And the red curve here corresponds to large values of direct. So this would be large values of direct, red curve, because the logistic curve is steepest for this type of email. All right, when an email does not have the word you in it, in other words, you is equal to 0, what types of emails are most likely to be safe? Well, focusing in at u equals to 0, we see that the highest probability of safe are emails with a large value of the word direct. So when u is 0, emails with large fractions of the word direct have the highest probability of being safe, at least compared to emails with smaller fractions of the word direct. What if u is equal to 10, way out here? Well, notice the story completely changes. It looks like that if u is a pretty frequently appearing word in the email, it looks like that the emails with the large values of the word direct have a lower probability of being safe than emails with a larger value here. So the story changes when u is equal to 10. Specifically, now emails with large values of direct have the smallest probabilities of being safe, with small and median values of direct having a higher probability of being safe. All right, F4 asks us to describe how the nature of the relationship between the probability of being safe and the frequency of the word direct changes as we consider emails with progressively larger frequencies of the word you. So we're being asked to describe the plot going on over here, and we're being asked to describe what changes about this curve as we consider emails with progressively larger values of the frequency u here. So we start out with small, so basically the blue curve. So the blue curve, u small, is showing there is a positive relationship between the probability of being safe and the frequency of the word direct as we consider emails with larger values of u. This relationship weakens. Notice that the black curve here for median values doesn't change quite as rapidly with the frequency of the word direct, so the association is getting a little bit weaker. And then it flips sign. So we notice that for the very largest values of u, the logistic curve actually has a negative relationship between the probability of being safe and direct. So at the largest values of u, the relationship is negative. The probability of being safe goes down as the frequency of the word direct gets larger. So pretty interesting. We wouldn't be able to capture that effect if we didn't have that interaction in there. Very often interactions, do play a very important role in relationships, and it's always useful to consider them. All right, part F5 says to refit this model without the interaction and to visualize it, just so that you can see that, hey, if you didn't have this interaction going on, then you would have missed out really on this key component of the relationship. So I'm just going to straight up copy and paste. Without that interaction, we assume that one curve fits all. Basically, the relationship between the probability of any particular predictor variable looks the same. The shape is the same. It might be translated from the left to the right, but the overall nature of that relationship remains a constant. So what we notice is that without that interaction, if we had neglected to include it in the model, we would have just come up with the conclusion that the probability of being safe and the frequency of the word direct has an overall positive relationship. Emails with larger values of the word direct have a higher probability of being safe. And we saw that by allowing that interaction, which did turn out to be statistically significant, we see the story is actually a bit more complex. Sure, it is positive when we consider emails with small or medium values of the word "you," but for emails with a high density of "yous" in it, it looks like actually the probability gets smaller of being safe as we look at emails with larger values of the word "direct." All right, in question 2, we're going to look at the EX9 store data frame. So let's go ahead and load that up. And in this data frame, what we have is information on shoppers' habits, whether or not they've gone and made a purchase at store 1, store 2, store 3. It's been anonymized. And the two levels of all of these variables, it's all either just buy or no. All right, so if we're going to develop a model that predicts whether or not someone, say, does shop at store 1, our two levels are buy and no, so our model is going to be predicting the probability of not shopping at that store. So something to keep in mind. All right, so what we're being asked is to fit a model that predicts store 68 from all predictors in the model. So let's fit that. GLM store 68 twiddle dot data equals ex9.store, and family equals binomial to turn on logistic regression. And we're going to get a summary of this model. And it's going to be a pretty big model. There's a lot of predictors here. All right, so every single predictor we have is categorical. Our response variable is categorical as well. And these numbers are going to allow us to help to compare different shoppers here. So part A says, among two shoppers with otherwise identical buying habits, in other words, they both shop at the same set of stores and not shop at the same set of stores, which one has the higher probability of buying at store 68? The one who buys at store 66 or the other one who doesn't buy at store 66? So, all right. Let's scroll down to store 66, and what we see is, first of all, this is a statistically significant predictor. So all else being equal, comparing two otherwise identical shoppers in terms of their values for store 57, 58, etc., we do find that there is a statistically significant difference in probabilities of shopping at store 66. So what can we say? It's best to reason this out since there's probably a lot of double negatives flying around. The coefficient is minus 0.60, or 0.6, let's just call it that. And so this is negative. That means the probability of the level of interest is lower when store 66 no equals to 1. That's our indicator variable representing this. Than when store 66 no equals to 0. All right, so I'm going to have to reason this through, so I'm just going to copy and paste this. So the level of interest is not shopping at store 66 here. That's basically what we're predicting. It's lower when store 66 no equals 1 than, store 68 here, than when store 66 no equals to 0. So store 66 no means that they don't shop at store 66. Shopper does not shop at store 66. Okay, so let's try to put this together. I'm going to copy and paste this again. We're being asked, who has the higher probability of buying at store 68? So what we can do is kind of flip some of these double negatives. The probability of shopping at store 68 is higher. So not lower is the same thing as higher. So the probability of shopping at store 68 is higher for the shopper that does not shop at store 66. All right, so interpretation of these coefficients can get pretty tricky depending on what your model is predicting, depending on what the levels of potentially an indicator variable is that encodes the categorical variable as a predictor. Sometimes you just got to write out basically what the definition of the coefficient is telling you and then kind of piece the interpretation together here. But because it's by no means obvious when I see a minus 0.6 here, does that mean the probability of buying at store 68, is that higher for store 66 shoppers or not? first of all, our model is predicting the probability of not buying at source 68. Then I have the indicator representing the level no. It's just a mess. You have to reason it through. All right, by running confusion matrix, comment on whether the multiple logistic regression model, is making predictions good here. So let's look at the confusion matrix. All right, is it more useful than the naive model? Well, let's look at the naive model first. So the naive model, that's majority rules. The naive model says, all right, if I look at the people that do buy and don't buy at store 68, I see the majority don't. So all 470 shoppers that did actually end up shopping at store 68 end up getting misclassified by the naive model. So 470 misclassifications out of 1,500 for a misclassification rate of 31.33%. Our logistic regression model, well, two types of errors it can make. It can either predict buy, but in actuality they don't, or it can predict that they won't buy, but in actuality they do. So we have a total of 122 plus 249 out of those 1,500 customers that our model incorrectly predicts for a misclassification rate of 24.7%. So yeah, our logistic regression model is much better than the naive model for making predictions here. Its misclassification rate is noticeably lower here. So model is much better than the naive model at making predictions. All right, C says, let's check to see if this is a reasonable reflection of reality here. So we'll look at the p-values of the test the assumptions, and it looks like that it is. So the p-values of both tests are bigger than 5%. So yes, this model provides a reasonable reflection of reality. All right, question 3 wants us to look at a new data frame that we're going to have to read in. So let's read.csv this, and this is called act10-account.dat. So if you do this and you get an error saying, oh, I can't find it, remember to have that file be in the folder that R is currently looking in. So right now, R is currently looking in a completely different folder in my BAS 471 class. And so I'm going to go to Session, Set Working Directory, choose my directory so that it's actually looking in the right place. And for me, it's in the Assignments Activity 10 folder. Boom, there's the data file. And now we can read this in. And this data frame is information about customers. We're trying to predict whether or not a customer will make a purchase for this new particular type of bank account based on their checking balance and branch of bank here. So what we're going to do is we're going to fit a model that predicts purchase from checking balance and branch of bank. No interactions here because I said let's just skip them for now. Because what we're really interested in knowing is there any difference in the probabilities of opening up this account based on the branch of bank here? Maybe some branches are more effective at convincing customers to buy than others. And, customers that have larger checking balances may have a higher probability of making this purchase as well. So let's compare otherwise identical customers in terms of their checking balances and then see if there's any leftover difference in probabilities between branch of banks. So let's fit our logistic regression model, and then let's run drop one. Let's see if the set of indicator variables representing branch of bank is statistically significant. Now, if this was just a two-level categorical variable, we could just look at the output of the summary. But since branch of bank has many different levels, we need the results of drop one here. So we run drop one. We see that it's represented by 18 different indicator variables. Is there a statistically significant difference in the probabilities between bank branches after we compare customers with equal checking balances? Well, yeah, absolutely. This p-value is much less than 5%. So, all right, if there is a statistically significant difference, we're asked to figure out which branch has the highest probability and which one has the lowest probability here. So, well, one thing that we can do is visualize it, just kind of see what this model looks like. This isn't going to really work all that great here because there's so many different levels, it's going to be hard to tell who has the highest and who has the lowest. I have no idea looking in here, which curve is up on top, which curve has the higher probability of yes. I can tell you that this pink curve here definitely has the lowest value. But is that B14? Is that B4? These colors look a little bit too similar here, so we need to actually look at the results of the summary. All right, so the coefficients of the indicator variables are telling us something about the relative probability between that branch and the reference branch, whatever level comes first alphabetically. And in this case, B1 is the reference branch, basically. We see that all the other branches get indicator variables, and B1 doesn't. It's the reference level. All these coefficients will be interpreted with respect to that particular level. All right, so we're being asked which bank has the highest probability of a customer purchasing this new type of account, assuming we're talking about customers with equal checking balances. And these coefficients tell us this. If we have a positive coefficient, that means that branch has a higher probability than the reference branch, branch 1 here. So if we just scan down this list and find the largest, most positive coefficient, that's going to apply. That's going to have the largest probability. So scanning down, this is by no means obvious here. This one is 0.13. That's pretty big. And do we see anything bigger? See anything bigger? No. Well, that's fortunate here. It looks like branch B10 has the highest probability. Its coefficient is the most positive, so it, in a sense, is the highest of all of them. So the branch for B10 must be the one that's up on top. Which has the lowest? Well, that's going to be the most negative, the one that's most below the reference level. And so which one is the most negative here? Well, we see a minus 0.9. Can we beat that? Can we beat that? No, we can't. So it looks like branch 14 has the overall lowest. B14 has the lowest probability. Its coefficient is most negative. And that confirms what we saw over here. B14, that's that pink line. All right, so without an interaction, the model's assuming a one-curve-fits-all approach. It's assuming that for every single one of these branches, the nature of the relationship between the probability of opening this account and checking balance is the same. It may not be the case. Maybe some curves could be really steep, other curves could change slowly. Maybe we should allow for the possibility that interactions exist, and therefore the nature actually is different depending on what branch we're actually talking about. So let's refit this model, allowing for the possibility that different branches of the bank might have different shapes for the logistic curves. So we'll run that, and we'll run the result of drop 1 again to see if there is any statistically significant interaction going on. We look at the p-value of the interaction, and we find that the p-value is less than 5%. So our conclusion is that yes, there are at least 2 branches whose shapes of these logistic curves are going to look different. Now, the test doesn't tell us which 2 are different. Maybe they're all different, maybe only 2 are different. The test stops short of actually telling us here. So let's actually run visualize model just so we can get a little bit of additional insight. And I'm going to put the legend on the right to make things slightly more clear. Okay, so here are these differences that we're talking about. It looks like this green branch, which is probably B9. It's hard to tell if it is this green one or this green one. There's 2 green ones here. But it looks like B9 has a negative relationship between opening the account and checking balance, while the other branches have positive relationships. Notice, however, this gray curve doesn't change all that much, so the relationship is pretty weak between opening up that account and checking balance. What is that gray branch? Well, it's hard to tell from looking at this. It's either B16 or B6. Let's call it B6. So B6, gray curve, looks to have a weak relationship between the probability and opening up the probability and checking account, checking balance. I'll label this a little bit green curve. Notice the other green curve has the strongest relationship. It's the curve that's up on top. And so whatever that curve is, let's call it B19 or B11. I'm not sure which one it is. You have to actually do the math to figure out which one's on top. The strongest relationship looks to be with either B11 or B19, another green curve. hard to tell which it is without actually going and writing out those implicit regression equations. And we're not going to do that because that would take really quite a bunch of work. As you see, there's a lot of output. So there we go.